Good morning, students. Today you are going to learn the thermodynamic properties, particularly the partial molar property or partial molar properties. The properties of substance system can be divided into two types. The properties of system can be divided into two types: extensive properties and intensive properties. The extensive property is the property which depends on the total amount of the substance or total amount of the different constituents of the system. For example, mass, volume, energy, entropy, free energy are extensive properties, and intensive property does not depend on the total mass or the total amount of different constituents of the system. For example, pressure, temperature, density, refractive index are the intensive properties, and today you are going to learn the partial molar properties. Okay, the total mass of the system is the extensive property, but mass per mole is intensive property. Volume per mole, energy per mole are also intensive properties. The total mass of a closed system and isolated systems are always remains constant. The change in any thermodynamic property is due to the change in state of the system, and all of you know the state of system is changed by changing the variables of the system, and system variables are pressure, temperature, concentration or composition of the constituents. Then, in case of open system, as mass and composition of the constituent present in the system can also vary, it is necessary to take into consideration the contribution of each constituent to the total property of the system. So, the scientist G.N. Lewis introduced the concept of partial molar properties for studying open system. Here, G.N. Lewis, the scientist, introduced the concept of partial molar properties for studying the open system. Consider an open system composed of I constituents, I number of constituents, and let n1, n2, n3 ni be the number of moles of constituents of 1, 2, 3 up to I present in the system. Here we have considered I number of constituents and n1, n2, n3 ni be the number of moles of constituents of 1, 2, 3 up to I number present in the system. Let X be the thermodynamic extensive property of the system selected for study. Here, in general, we consider X is our thermodynamic extensive property. Its value is determined by state of the system, that is the temperature and pressure, and the amounts of various constituents present in the system. It means the property X is a function of temperature, pressure and amounts of various constituents present in the system. Mathematically, it is written as X equal to f of p, t, n1, n2, n3 up to ni. That means this thermodynamic property X, it is the function of pressure, temperature and the number of moles of the constituents present in the system. Then The change in property dx due to small change in pressure, temperature and amounts of various constituents is given by here dx it is equal to dou x by dou p into dp at constant temperature and number of moles plus dou x by dou t into dt at constant pressure and number of moles plus dou x by dou ny into dny at constant pressure, temperature n2 dot dot ni plus dou x by dou n2 into dn2 at constant pressure, temperature n1, n3 and ni constants. That means here the second constituent is kept constant. Okay, we have taken other constituents as constant except second. Here the first constituent we may change and here we kept the all other constituents moles constant. Similarly, dou x by dou ni into dni at constant pressure, temperature n1 up to n minus n of I minus 1 constituent. Okay. Then the quantity dou x by dou n1 at constant pressure, temperature n2 dot 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 up to ni is called a partial molar property. Okay, this quantity dou x by dou ni at constant pressure, temperature n2 dot dot ni is called the partial molar property of the first constituent, and the partial molar property of the first constituent it is denoted by putting bar over the property, and here we have taken the first constituent. Our partial molar property is the x, so we have put here bar over the head of this x and it is denoted by this x1 bar. X1 bar it is the partial molar property of the first constituent. Then similarly we can represent the partial molar property of second constituent as dou x by dou n2 at constant pressure, temperature n1, n3 dot dot up to ni is called the partial molar property of the second constituent and is denoted by the x2 bar, and the partial molar property of the ith constituent we can represent as dou x by dou ni at constant pressure, temperature n1, n2 dot dot up to n of I minus 1 constituent, and it is represented as xi bar. Thus, in general, we can write x1 bar it is equal to dou x by dou n1 at constant pressure, temperature n2 dot dot up to ni, and x2 it is equal to dou x by dou n2 at constant pressure, temperature n1 comma n2 up to ni, and xi bar it is equal to dou x upon dou ni at constant pressure, temperature, then n1 n2 dot dot up to n of I minus 1 constituent. Then substituting these values in equation number 52, this is our equation number 52. This here we can substitute the value of dou x by dou n1 as x1 bar, here second constituent's partial molar property as x2 bar, and the ith constituent's partial molar property as xi bar. Substituting the values in this equation number 52, we can write this equation here. Dx it is equal to dou x by dou p into dp at constant pressure and here it is temperature at constant temperature and number of moles of the constituents plus here dou x by dt into dt at constant temperature and number of moles plus x1 bar into dn1 plus x2 bar into dn2 plus dot dot plus xi bar into dni. Then at constant pressure and temperature, the first two terms on the right hand side of this equation becomes 0 and we can write dx it is equal to x1 bar dn1 plus x2 bar dn2 plus dot dot plus x1 xi bar dni. Then from equation 53 it can be concluded that the partial molar property signifies the change in the extensive property X of the system with change in number of moles of the first constituent of the system at constant pressure and temperature when number of moles of other constituents remains unchanged. I repeat this equation 53, it can be concluded that the partial molar property signifies the change in extensive property X of the system with the change in number of moles of first constituent of the system at constant pressure and temperature when number of moles of other constituents remains unchanged. Or in other words, the partial molar property is the change in property X of the system at constant pressure and temperature when 1 mole of particular constituent is added to such a large quantity of system so that the added mole does not affect the composition of the system. I repeat, the partial molar property is the change in property X of the system at constant pressure and temperature when 1 mole of particular constituent is added to such a large quantity of a system so that the added mole does not affect the composition of the system. Then in particular we will see the partial molar volume. Here the partial molar volume of ith constituent of the system is given by this phi I bar. It is equal to dou phi by dou ni at constant pressure, temperature N1, N2 up to Nj, where Nj indicate number of each components except I are held constant. The partial molar volume can be defined as the change in volume of the system when 1 mole of ith constituent is added to large quantity of system at constant pressure and temperature, keeping number of moles of other components constant. Then we will see the partial molar free energy or chemical potential. The partial molar free energy, it is also called as chemical potential. Then the partial molar free energy of ith constituent of the system is given by the relation here Gi bar, where G stands for free energy and bar it is for the partial molar free energy and this I it is for the ith constituent. So the Gi bar it is equal to dou G by dou Ni at constant pressure comma temperature, comma N1, N2, dot dot up to Nj. Then the partial molar free energy is also known as the chemical potential, and it is denoted by the symbol mu. So we can write mu I, it is equal to dou G by dou Ni at constant pressure, temperature N1, N2, dot dot Nj. Then the chemical potential can be defined as the change in free energy of the system when one of ith component is added to a large quantity of system at constant pressure and temperature, keeping number of moles of other components constant. Then the chemical potential mu is an intensive property. It is a property which determines the reactivity of the system. A change in system at constant temperature and pressure will proceed from state of higher chemical potential to a lower chemical potential until its value is uniform throughout the system. Then for a binary mixture, the change in free energy is given by the relation. Suppose we have two chemical constituents and we can write the change in free energy as dg, it is equal to dou G by dou P into dP at constant temperature and the moles of the two constituents plus dou G by dou T into dt at constant pressure and number of moles plus dou G by dou N1 into Tn1 at constant pressure, temperature and N2 plus dou G by dou N2 into Tn2 at constant temperature, pressure and N1. Then at constant pressure, temperature, these two terms they becomes 0 and we can write here dg at constant pressure and temperature, it is equal to dou G by dou N1 plus dN1 at constant pressure, temperature and N2 and dG by dou N2 into dN2 at constant pressure, temperature and N1. But we know mu1 it is equal to dou G by dou N1 and mu2 it is equal to dou G by dou N2. And mu1, mu2 these are the chemical potentials of constituent 1 and 2. Then substituting in equation number 62 we get dg at a constant pressure, temperature, it is equal to mu1 into dN1 plus mu2 into dN2. Let it is our equation number 63. On integrating equation number 63 we get free energy at constant pressure and temperature, it is equal to mu1 N1 plus mu2 N2, or in integral here free energy at constant temperature and pressure, it is equal to summation of mu I Ni for a single pure component. Then here we can write the chemical potential means free energy at constant pressure, temperature, it is equal to N into mu, it is equal to N into G bar, and here mu it is the G bar and it is equal to G by N. Therefore, for a pure substance, the chemical potential is given by its free energy per mole. Remember, for a pure substance, the chemical potential is given by its free energy per mole. Then the variation of chemical potential with pressure and temperature. Here at first we see the variation of chemical potential with pressure. Here mu I, that is chemical potential of the ith constituent, it is equal to dou G by dou Ni at constant pressure and temperature. Okay. Then differentiating with respect to pressure at constant temperature and composition, we can write dou I by dou P at constant T and Nj, it is equal to d of dou P into dG by dou Ni. The variation of free energy with pressure at constant temperature is given by dG, it is equal to phi dP, or dou G by dou P, it is equal to phi. Then the differentiating with respect to Ni at constant temperature and composition, we can write dou Ni into dou G by dou P into at constant temperature and number of moles, it is equal to dou V by dou Ni, and it is nothing but partial molar volume. And from equation 68 and 69, we can write dou mu I by dou P at constant temperature and the number of moles of the constituent, it is equal to mu I. It is equal to partial molar volume of the ith constituent. This signifies that the rate of change of chemical potential with respect to pressure of any component of the system is equal to partial molar volume of that component at constant temperature and composition. Okay, this equation number 70, it signifies that the rate of change of chemical potential with respect to pressure of any component of the system is equal to partial molar volume of that component at constant temperature and composition. Then the variation of chemical potential with temperature. Here we have mu I, it is equal to dou G by dou Ni at constant pressure, temperature, and N1, N2 up to Nj. Differentiating this equation with respect to temperature at constant pressure, we can write dou mu I by dou T at constant pressure and number of moles, and it is equal to dou by dou T into dG by dou Ni at constant pressure and number of moles. Then the variation of free energy with temperature at constant pressure, it is given by dG, it is equal to minus S dt, or dou G by dt, it is equal to minus S, means entropy at constant pressure. And differentiating with respect to Ni at constant pressure and composition, we can write this as minus Si bar, that is the free energy, partial molar free energy of I constituent. Okay, and this equation signifies that here the rate of change of chemical potential with respect to temperature of any component of the system is equal to partial molar entropy of that constituent at constant pressure and composition. Okay, this dou mu I by dt at constant pressure and number of moles, it is equal to minus Si bar, where Si bar, it is the partial molar entropy, and this equation signifies that the rate of change of chemical potential with respect to temperature of any component of the system is equal to partial molar entropy of that constituent at constant pressure and composition. And let us focus on the Gibbs Duhem equation. This is the very simple and related to chemical potential equation. Okay. Here, consider an open system composed of I constituents. Let N1, N2, N3 up to Ni be the number of moles of constituents of 1, 2, 3 up to I present in the system. The free energy G of the system is an extensive property and it is a function of pressure, temperature and amounts of various constituents present in the system. And mathematically we can write as G, it is equal to F of P, comma T, comma N1, N2, N3 up to Ni. Then the free energy change due to small change in pressure, temperature and amounts of various constituents, we can write dG, it is equal to dou G by dou P into dP at constant temperature and number of moles plus dou G by dou T into dt at constant pressure and number of moles plus dou G by dou Ni into dNi at constant pressure, temperature and N2 dot dot Ni. Then plus dou G by dou N2 into dN2 at constant pressure, temperature N1, N2 up to Ni plus dot dot plus dou G by dou Ni into dNi at constant pressure, temperature N1, N2 up to Nj. Okay, but mu I it is equal to dou G by dou Ni at constant pressure, temperature and the N1, N2 dot dot up to Nj. At constant pressure, temperature, this equation can be reduces to the two right hand terms, they becomes 0 and we can write the change in free energy at constant pressure, temperature, it is equal to mu1 dN1 plus mu2 dN2 plus dot dot plus mu I dNi. And integrating this equation, we can write G free energy at constant pressure, temperature, it is equal to mu1 N1 plus mu2 N2 plus dot dot plus mu I Ni. Let it is our expression number 77. Then general differentiation of equation 77, we can write here dG at constant pressure and temperature, it is equal to mu1 dN1 plus N1 du1 plus mu2 dN2 plus N2 d mu2 plus dot dot plus mu I dNi plus Ni du ui. On rearranging, we can write dG at constant pressure, temperature, it is equal to mu1 dN1 plus mu2 dN2 plus mu I dNi plus N1 du1 plus N2 du2 dot dot plus Ni dui. And comparing equation number 76 and 79, we can write Ni dui plus N2 du2 plus dot dot Ni dui, it is equal to 0, or summation of Ni dui, it is equal to 0. And this equation is called as Gibbs Duhem equation. It is very important in the study of chemical potential of binary systems, solutions, liquid vapor equilibria, phase equilibria, etc. For two component system, equation 80, it becomes as Ni d mu I plus N2 d mu 2, it is equal to 0. Therefore, N1 d mu 1, it is equal to minus N2 d mu 2. Therefore, d mu 1, it is equal to N2 minus N2 by N1 into d mu 2. And this equation shows that the change of chemical potential of one component brings about the change in chemical potential of the other component of system. Negative sign indicates that if chemical potential of one component increases, then that of the other decreases, but the total sum of change of chemical potential is always 0. Okay, and depending on, you may ask the problems, okay, to solve this. So prepare well, and if you have any kind of doubts, then you may ask me. Thank you for your patient listening.